Welcome back. So we are now going to move on with the lecture. But before we go to data modeling, I have a top 10 for you. Let's look at the data technology stack again, right? So this is what we are trying to rebuild. And we've already done part of it. So storage, encoding syntax, data modeling, we did a little bit with HBase in the sense that we look at the relational model. But today we are going to not only look at denormalized data for the data modeling, and we are going to validate that data. So you see, we are just climbing up our technology stack. All right, but let me do a top 10. I would like to summarize a few of the lessons that we have learned so far in the big data lecture since the very beginning of the lecture, the high-level lessons that will also drive us through the rest of the lecture. The first lesson we've learned is to learn from the past. There is so much that our ancestors have done. They have made mistakes that we don't need to repeat, so we can learn from them. And in that case, it means with relational databases. Relational databases are 50 years old. We can learn a lot. So this is why we looked into SQL, into normal forms, the relational models that is also there in HBase and so on. So we need to learn from the past. This is also a message to the JSON community that there is this apparent antagonism between JSON and XML. So it's very frequent to hear that XML is not so great because it's too complex and JSON is better. But nevertheless, the XML community has invented a massive technology stack, and they've made a lot of mistakes doing it and fixed the mistakes in order to get to that state. The JSON community would have a lot to gain by looking into what the XML community has done in order not to make the same mistakes. That way, they can massively accelerate the development of the JSON technology stack by learning from what was done on the XML side. And I think it's not done enough. What has happened in the past few years is that they have repeated some of the same mistakes. And I think we can really gain several years by looking into what other people have done because they are more similar than they seem. So learn from the past. Second, keep the design simple. This is why we have key value models all over the place. We have them in object stores, in S3, we have them in HDFS, we found it also in JSON objects, in XML attributes, and we even saw them in HBase when we looked at a store that is also stored in an H file as a list of key value pairs. So we love key value pairs in big data because it's pretty simple, and we love to keep the design simple. If you look at the design of HDFS, super simple. The logical level of HBase, super simple. It's the physical implementation that is complex, but this is all hidden from the user. That's the beauty of it. I'm also showing to you, of course, the physical implementation, and sometimes it can feel a bit scary. I mean, I know that the HBase lecture is one of the most complex ones of this course. But you really need to understand that that scary part is the hidden part, right? And what is the visible side of the iceberg that people actually see is, in fact, usually very simple. So this is how we scale. Then we modularize the architecture. That's what I explained with this Mensa analogy, right? So we really have multiple layers on our stack. We have HDFS, we have HBase. We'll see that we'll have extra layers, MapReduce, Spark, JSONic, and so on. So this is what computer scientists love to do. This is exactly like when you build a house. You have the masonry, the plumbing, the electricity, and so on and so on. And this is just nicely modular, and this is how you optimize doing that, right? So we love to modularize the architecture. What we saw then, number 4, is the homogeneity in the large. It means that when you look at very large scales, things look homogeneous. For example, in HDFS, you can have billions of blocks. In HBase, you can have billions of rows, millions of columns, you know. It all looks homogeneous, basically. And when you have this homogeneity in the large, we see that's another of the point we can start sharding, right? But basically, for big data, at very large scales, things are very homogeneous. But at small scales, things are heterogeneous, a bit like classical physics versus quantum physics, right? At small scales, things look different. So while at large scales, it looks the same, at small scales, when you denormalize your data, this is when you start seeing that the individual JSON objects might actually not look all the same, and each one of them has its particular properties that makes it different, right? So it's some of a database diversity, if you want to call it that way, right? And in big data, this is extremely important because this is a new development. It's unlike relational databases where it was also heterogeneous, but homogeneous in the small. But in big data, we can absolutely denormalize the data and allow for different structures locally, right? And it is this duality between the homogeneity in the large and the heterogeneity in the small that drives the design of big data systems. Another thing we do is that we love to abstract the logical model from the physical implementation, and I do it in every lecture. I start with the logical model, and then I tell you how it's implemented, right? And that part is actually hidden. 7, that's the benefit of the homogeneity in the large. We shard the data. I even give you plenty of words for that. There's shard, block, split, partition, chunk, and there's probably even more, right? So there are so many terms to call it. When you have billions or trillions or quadrillions of something, you really have this irresistible urge to shard it. You just have to do these smaller shards, and this is how you can distribute it across machines, right? So we shard the data all over the place. We've done it so far, and we'll continue to do it in many, many weeks to come that we just keep sharding data. Then we also love to replicate the data. This is because we don't want to lose it, right? So we have replicas of the HDFS blocks. We have also this write-ahead log that it was true, it replicates the data, right? But this is just taking precautions in case of a power outage or an earthquake. You know, we just like to be extra careful. So we also replicate the data. And since we sharded it, it makes it also easier, right? Because then we just replicate the shards of the data. Lesson number 9, we love to buy lots of cheap hardware. We don't try to buy an enormous, gigantic computer. We just buy thousands or millions of small computers. This is what we do. And this is what there is in data centers. I demystified it. There are just thousands of computers like that are nicely piled up on top of each other in racks. And then the racks are put together in a room, right? And finally, the last principle, maybe I didn't insist on that, but this large structures merge tree, this is the batch processing that I told you about. Batch processing is this idea that it's like this 2048 game, as you mentioned, we just do it one chunk at a time, right? So we batch process by writing at the same time an entire H file, and then when we compact, we do it at the scale of H files. We do not do it at the scale of individual values because that would be highly inefficient, right? So the batch processing is to just process values, billions, millions, or billions maybe not billions, millions at the same time. We love to process values in groups of a few millions, all right? Okay, I'm done. These are the 10 lessons, and you will see it's not going away. We'll just have this for even more weeks. These 10 principles, I think, are really driving the field. All right, so let's now make progress and move on. I told you we've taken care of that. We kind of started taking care of that with the relational model, but today we'll focus on the denormalized data, right? I kind of started that with JSON and XML, right? I explained to you that JSON and XML are a way to denormalize data, and we looked into the well-formedness of JSON and XML. But now what I want to do is look into also the validation of that data that's going to come after that, because then we can make even more explicit that it's denormalized data. All right, are you ready? So let's go. I need to insist, even though I already did that a bit, on this difference between two levels. There is the syntactic level where we have here it's CSV, right? And we have the logical level where this is a human, this is what we see in our brain, right? Or the way we put it on a screen in such a way that it looks fancy, right? So here it's boring, it's just text, comma separated values, but of course the magical power of our brain represents it like that, giving us a logical view. This is in fact a data model. It's a data model with the rows, the columns, and so on and so on. Well, we are going to now do the same thing with JSON and XML. We are going to find a logical view like this to represent JSON and XML data. All right, so let's start with JSON. What do we have in JSON? Well, you remember from 2 weeks ago, we have 6 building blocks: strings, numbers, booleans, null. These are the atomic values. And we have objects and we have arrays, right? So the objects, we remember it's the key value model, and the arrays is just an ordered list of values, right? Okay, and we have the recursion because whenever you see a list of values or a map of keys to values, then a value can again be any of the 6. So this is how you get the nesting and the denormalization. All right, but now let's get to the visual. In the same way that a CSV file can be opened into a spreadsheet software and viewed as a table, what will I get if I try to draw a logical view of that? Will I get a table? What will I get? Hint, the answer is on the slide. What do you see here in your brains?
Yes, please. Tree.
Yeah, exactly. So let's draw a tree then. That's exactly what we are going to do. What's the top level? It's an object, right? All of that is an object. So let me just represent that as the root of my tree. I have an object. Okay. Now, what are the children? In a tree, we have children and children and children, right? It's like a genealogical tree. So how many children do we have? Well, let's look. We have a key value model with 2 keys, foo and bar, right? All right, so I have foo and bar. These are my 2 children. Foo points to true. So these are my nodes as rectangles, right? These are my values. So the value true, the value object. True in here is associated with the key foo to the object. And here we have an array. You see the array here, square brackets, is associated with bar. So I have an array associated with bar. Okay, true, that's a leaf. It's an atomic value. There's no more children there, right? True, we reach the end here. But array has some recursion left. There is something inside. How many? 1, 2. There is an object and there is a null. So we have an object and we have a null. Okay, here it stops. That's a leaf because null is an atomic. But here we have an object that continues. How many children? 1, foo bar, associated with the value foo. And here it stops again. Foo is an atomic value. So the data modeling that we are doing today is really about, out of a JSON document or an XML document, we want to draw a tree representation of that document. Why are we doing that? Because that tree here is the level of abstraction that will then allow us to query the data, right? And we need that extra layer of abstraction. We cannot just keep looking at text documents, right? This is too low level. So this is why we love to work at that level. One of my learning objectives is that I would like you, when you look at a JSON and an XML document, to immediately and spontaneously see this in your mind without even having to draw it. If you look at this, this is what I want to have in your brain when you look at this. For whom is that already the case? If I give you this, you actually see that tree. Can you raise your hand just for me to get an impression in the lecture hall and in the chat?
I see a couple of hands in the lecture hall.
Very nice. So already a few of you. So train that. You will have exercises to do that. This is my objective. I would like you to see the tree, basically. I want you to see the trees. Okay. So now we did the same thing as with CSV, except now we have JSON here, and we have our logical view, the logical model. That's the data model, right? Okay, turns out we can do the same with XML. So if I have an XML document right there with elements, nested in elements, I can also draw a tree like that. That's nice. So you see now why I kept saying that JSON and XML are really the same thing, because it's just trees and trees, right? It doesn't really matter if it's JSON or XML. At the end, you get a tree. Okay. So of course, there's a few differences between the tree that you get with JSON and the tree that you get with XML. It's a bit subtle, but there are a few differences. And one of the difference in JSON, let me put it that way. In JSON, a value does not know its name. So if you have, for example, here, true here, does not know that it's called foo. True is just true, right? So the foo is outside, it's on the edge from object to true. So if you just take true on its own, it doesn't know it's called foo. This array doesn't know that it's called bar. So this is what I mean here with the fact that we have the names on the edges and not on the nodes. In XML, it's different. If you look at an element in XML, an element always knows what it's called. if you have an element, it's going to be the element foo, the element bar. So it means that the actual names are not on the edges like this; they're actually on the nodes of the tree, right? So this is a major difference between JSON and XML. Maybe it's good, maybe it's bad. Actually, it turns out to be great for JSON because this is how we get data frames, as we will see. But XML also can make a lot of sense when you want to deal with taxonomy and artificial intelligence, ontology-based research. Then this is where this actually can become powerful, that the elements know their names. All right. Okay. So let me just continue to draw trees, right? We'll just draw plenty of trees today. So let me draw one more tree for XML to introduce you to the data model. The data model for XML, the first one that was created, is called the XML Information Set. It's basically a specification that explains how to draw a tree out of an XML document. That's pretty much what it is. Of course, it's a very long specification with a lot of details, but I'm just going to do it on the high level for you. And really, it's about drawing a tree. So let's take this document right there. That is an XML document. It's well formed, right? You recognize the optional text declaration, the declaration that the root is called metadata. And here we have elements, we have attributes, we have text, we have text. Who sees a tree here? I'm pretty sure several of you already see the tree. Not so many, right? Okay, so let's draw the tree together then. All right, so here's how it goes. In this specification called information set, there's 11 kinds of nodes that you can have in the tree. They are here. But don't worry, we are not going to look at all 11. We are just going to look at 4 of them. That's already more than enough for what we need. And you will see that these 4 actually correspond to something we've already learned when we looked at the syntax. Because guess what? We have elements, you know elements, right? We looked at them 2 weeks ago. Attributes, you also know attributes. We looked at them 2 weeks ago. And text, that's also something you know, right? So elements, attribute, text. And documents, that's the easy one. You could consider it's the doc type, basically, that appears here. It's just the root of the tree, right? It's just the thing we put at the top that holds everything else. So we have documents, elements, attributes, and text, and that's it. And we're just going to draw a tree with just these 4, and you can just forget and not even care about the rest. Just forget it. That's not even part of the course or the exam. All right. So elements, attributes, text, and documents. Let's do it then. Let's start coming up with the nodes. So I will keep displaying that document right there. So let's start with the root of the tree. The root of the tree is called the document information item. Well, information item, everything is called an information item, right? So, but here it's the document information item. I'll just put it in purple, writing doc inside. And it's a tree, so it has children. So what is the child of the document information item? Well, it's the top level elements. And in that case, the top level element is metadata, right? So the child of the document information item is the element information item, metadata. And then I have more properties like, okay, it's version 1.0 of XML and so on, but this is just secondary. All right, so we have the document and the metadata element. Okay, now let's look at the metadata element information item. So again, everything is called an information item, as I said. Now it's an element information item called metadata. So what do we have? Well, the local name is metadata. I didn't put namespaces. I mean, it's already complicated enough, so I didn't put namespaces. So the local name is metadata. What are the children of metadata? Well, we just look here. We have title and we have publisher, right? So we have 2 children, title and publisher, and these are also element information items, right? Just like metadata. Attributes, nothing, right? You see, there are no attributes in there. Just immediately close the tag there. And the parent, because we also go back the other direction, the parent was the former one here, the doc, right? So it points back to doc, okay? So now let's dive into these 2. So let's look into title. So title is this one right there, right? Title. Okay, so the element information item title. What is its local name? It's title, right? What are the children? Well, let's look at the children. The children, it's just, there's no nested elements in there. It's just systems group, right? So that's just a bunch of text here called systems group. I put it in black right there. So it's the text information item that contains the character systems group, okay? Now, what are the attributes? the attributes, we have two, language and year. So language is EN, English, and year is 2019. So I put these two attribute information items in there. And the parent is the element information item, metadata. Yes, the parent of publisher is metadata. Okay, I've done title. Let's do publisher now. So the local name is publisher. The children, well, it's just text, ETH Zurich, right? The attributes, well, there is nothing. There is no attribute there, right? Simply. And the parent is metadata, right? The parent of publisher is metadata. All right, now let's look at the attributes. Year 2019. Let me look at year 2019. The local name is year, right, of the attributes. The normalized value, yeah, normalized just means that if there's extra spaces at the start and end, you just drop the spaces, right? It's just some cleaning up if you want. So the normalized value 2019, right there. And the owner element is just a fancy name for parent, but the owner element is title because the attribute year appears in the title element. Okay, then the language EN, that's the other attribute right there. Well, the local name is language, the normalized value is EN, and the owner element is title. And finally, the text information item, system group right there. Well, you have the characters, so here it's boring, it's one by one. SYSTEMS space GROUP, right? So these are all the characters. And the owner element is title, right? System group is in title. Then we have ETH Zurich. So again, the characters are ETH space ZURICH, right? Right there. Inside the publisher owner elements, that is the element information item. Okay, so I've just presented to you the nodes of the tree. These are all the nodes of the tree, right? And there's 4 kinds of them. Document information item, element information item, attribute information item, and text information item. As promised, right? This is the promise I made you. Document, element, attribute, and text. Okay. So what do I do now? Well, let me draw the tree then. All I need to do now is look at these children and parent and so on, the owner element and so on, and draw the tree. And here I go. This is the tree. So every time you have children that points down and parents that points back up, right? So you have attributes that point down and also owner elements that points back up. I thought my green screen was collapsing, but no, it's not. Okay, so now this is the tree that we drew from that document, and the XML information set, or it's also called XML info set, is basically a specification that tells me how to draw a tree. You have, that's really part of the lecture. If you see JSON or XML, you must be able to draw a tree, right? That's how it works. And ideally, you must be able to directly see it in your head without even having to draw it, right? This is a goal, a learning goal, a learning objective of the lecture, right? So I know that some of you already do that automatically. If you do not yet do it automatically, just take documents, JSON or XML, and try to draw trees, right? Okay, JSON is actually easy. Actually, JSON is so easy that nobody even had the idea of coming up with a JSON information set, because it's actually so trivial that many consider that the original JSON syntax specification already implicitly draws the tree, right, in the way it's written. So this is why nobody even bothered to write a specification about the JSON information set. It's just trivial. Okay, any questions so far? No questions, so that means everybody understands everything I'm telling you. That's wonderful if that's the case. Okay, I think that lunch is approaching, right? Probably starting to get hungry, and that's okay. Okay, so let me move on then. Now that we have drawn trees, we would like to go to the next level and start validating data. What is validating data? Well, if I have millions of trees or billions of trees, if I don't enforce anything, it can quickly become an enormous mess, because I just have billions of trees that basically have all kinds of names and structures and so on. So if I want to have some homogeneity in the large, as I told you, you might want to ask that the trees resemble each other. They can still vary, of course, they can still have their own characteristics, but the overall structure of the trees is going to be similar. This is the process of validation. So Validation comes after well-formedness. Well-formedness, that's what we did 2 weeks ago, right? When we looked into well-formed JSON, well-formed XML, and now we move on to validation. Validation can only happen after well-formedness. If a document is not well-formed, that's over. You cannot even ask if it's valid. But if a document is well-formed, JSON or XML, then you can ask, okay, is it also valid or is it not valid? Right? However, well-formedness is universal. There's only one way. If your JSON well-formed, there's only one way to be. XML well-formed, there's only one way. Valid, that depends on your constraints. And you decide what constraints these are. So you need, that's called a schema. So you provide a schema that is the pattern that your document has to follow. And with a given schema, you can ask, okay, is that well-formed document also valid? Or is that well-formed document invalid? Right? So it's again a yes/no question, but this time with a schema. So it turns out that in Oxygen, again, I recommend please download Oxygen from the IT shop. ETH purchased the site license for us. I negotiated for several years in order to get there. Please download it and use it. It can be also very useful for later if you have research projects and you need to process XML, JSON, or quickly query it. You have, it depends on the version, of course, it keeps evolving, but typically it's like the matrix, right? Blue or red. The blue is for the well-formedness. If you click in here, then it shows you yes or no. There's a green flag that says, yes, it's well-formed, or there's a red flag that says, no, it's not well-formed, and these are the errors. And the red flag is for validity. So if you click here, then it will ask you, okay, which schema do you want to use, of course, and if you supply a schema, then it will tell you yes or no, the document is valid, or if it's invalid, then you will get the errors of validity errors. Okay. So blue for well-formedness, red for validity, and please try it out. Also in the exercises, you'll have an opportunity. Okay. What we also like to do in validation is we like to look at the type of the data. You saw that in XML, there's only text. There is no number or date or so on, or Boolean and so on as there is in JSON. So in the schema, you will typically say, okay, that element must be a date. That element must be a string. That element must be a Boolean, and so on and so on. So what you do is that once you have the tree that you got from the well-formed document and you validate it, then what you will do in the tree is annotate. You will basically replace the text with typed data. For example, you had the text 2019, and then you validate it saying, okay, that's supposed to be an integer. Then you will replace that text with the integer 2019. This is the validation, the annotation part, right? And this is how you prepare it for querying at a later stage, all right? So now, coming back to heterogeneous and homogeneous data sets, the idea is that if you don't have any schema, and that's absolutely fine, you're totally free to not have any schema, you just drop your data on HDFS without validating, that's absolutely fine, then it's heterogeneous. If you apply a schema, you can check that your entire collection, your billions of documents, all match against the schema, and then it's homogeneous. Example. This here is something messy. I actually did it, I made it up on purpose just to show you if you don't have any schema and let the data basically have its own life, then you see here I merge a lot of things. There's a string, there's a Boolean, there's null, there's objects. Here there's an integer, an std array. So here it's a bit of a mess. And this is fine. That's the beautiful world of big data, is that we're fine with that. You can also say, okay, for now, let me store the data like that, and I'll worry about cleaning it up later. Right? For example, if you want to feed it into machine learning pipelines, you'll need to clean it up. But we'll learn how. Right? And one of the first things you do once you have cleaned up your data a bit, so imagine I clean that up, then I get something like this. So you see, this is messy, this is a bit more cleaned up. Right? How do I see it's cleaned up? Well, look here, it's an array of just integers, and here and here. Here, there's every time an array of objects, and every object has foo, has bar. Foo is a string, bar is an array. So if you clean up your data in such a way that it has this structure, then here you can actually apply a schema and check that this document here matches against the schema. And I will show you what these schemas actually look like. Okay. Any questions so far? No questions. or maybe you're hungry. Okay, so just again, this is without any schema. It's a bit messy, and here it's cleaned up, and here we can apply a schema. All right. So now let me spend time telling you about these types, because when you have a schema, you're very often going to require that this value has to be an integer, or this value has to be a date, or this value has to be a Boolean. This is typically what you do when you want to use machine learning, right? When you want to have features and you want to have here, it must always be a date, it must always be an integer and so on. So you have to know a bit the type system in order to do that. So let's explore types. But the beauty of types is that it's kind of universal, is that it doesn't matter if it's JSON, it doesn't matter if it's XML, it doesn't matter if it's a CSV, it doesn't matter if it's the future technology or whatever. The nice things with types is that there's generic principles on them that are kind of universal. So I'm just going to go through the types without having in mind JSON or XML or whatever. It's just generic, and then you can learn any schema language with this knowledge on types. So, and the reason is that almost any type system, that even includes programming languages like Java, SQL, that's just the annotated XML after a schema, that's the JSON data model we use later. Protocol buffers is a Google technology that is for storing trees. Avro and Parquet are binary formats for storing data similar to JSON. I'll come to it. But basically, all of them share common features, and that makes it super easy to learn. So what are the common features that they share? First, they all distinguish between atomic types and structured types, all of them. That shouldn't be new to you. We already saw that in JSON. For example, the atomics are string, Boolean, numbers, and null, and structured is object array, right? It's the same thing in Java. If you program in Java, you know you can have ints, booleans, and so on that are atomic types, and the objects in Java are the structured types. The same goes in Python, and so on and so on. Almost any type system has this notion of atomic versus structured. Second, the categories of atomic types, they're more or less always the same. And I'll go a bit through them as a journey, but you'll find the same things into any language. There's minor differences, but it's really the same. So this is why we say you've learned a language, you've learned them all. It's really easy. Then the structured types are very, very often lists and maps. Right. So this is the key value model, the maps, it's the JSON objects, and these are the JSON arrays. But the abstract name for JSON object and JSON array is map and list. That's the theoretical computer sciencey way of calling them. But it's always almost lists and maps. And finally, we can have sequences of objects. So maybe not in Java, but in SQL, you can have tables that have plenty of tuples. And then you have the notion of cardinality. What is it, cardinality? Well, it's one value, one or more values, and so on and so on. Okay, so just let me check the time. Okay, I have 1 or 2 more minutes. So in general, we distinguish between atomic types and structured types across languages. The atomic types, what do we have? Well, first we have strings in almost any language. So I won't say much about that. A string is just a sequence of characters, right? That's just text. Right. So these are strings. This is one possible atomic values. Then we have numbers. What can numbers be? Well, there's integers, and the integers, as you know, end up as zeros and ones on your computer. So you probably know that in almost any language, Java, maybe Python simplified it now. They actually just have this int thing. But in older languages, you have 8 bits, 16 bits, 32 bits, 64 bits, byte short, int long, you might have heard of. These are just integers encoding on as zeros and ones on your computer. All right? Then you have arbitrary precision decimals that also exists. Well, you cannot do it in any language. I think in Python you can. In XML and JSON you can as well. So it basically means you can have any precision. You can write your decimals like that with absolutely any level of precision. And finally, you have float and double that are approximated real numbers that squeeze an approximation of a real number, in the case of float single precision, with a precision of 7 digits. And with 64 bits, it's called doubles in some languages, you have a precision of 15 digits, right? So this is just a way, there's the exact representation that takes a lot of space, and there's the squeezed representation with a precision of 7 or 15 digits, right? Okay, I'm going to stop here for today, right? So we covered strings and numbers so far. and we'll continue the journey of exploring types and validation next week. Before you go, I just want to ask you if you followed, and then you're good to go. All right, sharing my screen. All right. So this is actually it. So thank you, Wenxi, for moderating this lecture. I hope you learned a lot of things today. I know some part of it was quite complex. So congratulations for understanding what I told you regarding HBase. That's one of the most complex lectures of the semester. And next week we'll continue to draw trees and validate trees, and then we'll draw data frames out of valid JSON. We'll see that when you validate a JSON collection, you actually get data frames. Okay, so thank you very much. Thank you, Wenxi, for moderating, and see you next week.